In the last video, we talked about frequency distributions and histograms. Histograms being a graphical display where we indicate the counts or percentages using area. This video is going to continue that lecture by discussing some special types of histograms. We're going to establish a vocabulary for describing histograms. And let's move on to the next slide. So the next slide gives us data from the Old Faithful geyser. So this is a geyser that's located at Yellowstone National Park, and it's called Old Faithful because it erupts, very regularly, and it squirts water out of the ground for a couple minutes. And what you have in this slide is a list of the durations of about 99 eruptions. So you see the first eruption lasted 4 minutes, 4.37 minutes, the next one 4.70, and so forth. If we create a histogram, you can see a histogram below. And what you'll note is that there's a pretty distinct spike that spans from about 1.5 minutes to 2 minutes, and then there is a much larger spike that's out here at about 3.5 to 5 minutes. So clearly there are two types of eruptions that you might see if you visit Yellowstone National Park. One is kind of a short one, the other one is kind of a longer one, and the lack of area between, say, 2 minutes and 3.5 minutes means that there aren't many eruptions that last between 2 and 3.5 minutes. They're either shorter, 1.5 to 2 minutes, or longer. Such a distribution that has two distinct spikes is going to be called a bimodal distribution. Now, we'll learn about modes shortly. A mode is the most frequently occurring value in a distribution, so perhaps we would want to call this a bilocal modal distribution, in that within this region, this is the local mode. Within the higher region, this is the local mode. So this has two distinct spikes. If we kind of smooth away the spikes, you get this nice continuous curve, and you see it very clearly. Now, remember, histograms work on area. That's really important. So you have a ton of area off to the right, substantially less area on the left mode, which indicates that the longer eruptions are much more common than the shorter ones. So that's an example of a bimodal distribution. We're not going to spend any time on this next slide. Instead, I ask you to look at it on your own. So here's a frequency distribution for another question from the California Pizza Kitchen survey. The question asks, how many times have you visited any other casual dining restaurant in the past 30 days? What I ask you to do is to look at the frequency distribution and tell me if you see anything that's unusual, anything that doesn't make sense. Just make note of that. There's some graphs on the next page. Let's skip those. And let's move ahead to the shapes of distributions. So we've already discussed bimodal distributions. Here are a few other shapes that commonly occur. So we've seen normal distributions before. Here's a picture of a normal curve. With a normal curve, you have a single mode, and then on both sides the distribution falls off to some tails that extend out actually to infinity. So it's very unlikely that a person will observe a value out here in the tail, and that's indicated by the fact that there's very little area out there. Most of the values sit in this region here, the central region. So anytime we have a histogram that has this normal shape, we'll call it normally distributed. Another fairly common distribution is called the uniform distribution. The uniform distribution is completely uniform in that all the values between the minimum and the maximum have the same probability. Such a distribution might arise if, for example, we were to roll a fair die, say 1,000,000 times, and then count the number of times that a 1 came up or a 2 came up all the way through a 6. If the die is fair, then we would expect the same number of each of those numbers to pop up. And the graph of the histogram would look flat, completely flat like this. Another situation where you will encounter normal distributions is whenever you generate a random number from Excel. So if you use the default random number generator there, it's going to return a random number between 0 and 1, meaning any value between 0 and 1 is equally likely to come up. So these are both examples of something called a symmetrical distribution. So symmetrical is another term that you should know. What symmetrical means is that if you chop the distribution in half, the right-hand side looks like a mirrored image of the left-hand side. So let's chop this normal curve in half. So imagine a line. I'm going to fold this graph over on itself, and what you'll see is that this right-hand side is just a mirror image of the left-hand side. So that makes it symmetrical. Likewise with uniform distributions. If we were to chop this in half, the right-hand side is just a mirror image of the left-hand side. So those are both symmetrical distributions. The Old Faithful geyser data is not symmetrical because the right mode was substantially larger than the left mode, so that would not be a symmetrical distribution. It's possible to have a symmetrical bimodal distribution, but the Old Faithful data was not an example of that. When you don't have a symmetrical distribution, often you'll have something called a skewed distribution. There are two broad classes of skewed distributions, and you have pictures of them on the bottom of the slide. So on the left, you have something called a right skewed or positive skewed distribution. The other one shows a left or negative skewed distribution. How do you tell them apart? Well, the way I always tell them apart is to ask myself, where is the tail? So with the right skewed distribution, what you're going to see is that there's a long tail on the right. So the vast majority of the values are quite small, and then you have this long right tail. These right skewed distributions are extremely common in marketing. In fact, I would say that in my work with marketing data sets, I see more right skewed distributions than anything else. Whenever you have a count or an amount variable, you should suspect that it's going to be right skewed. So for example, if we had a copy of the American Airlines frequent flyer database and we looked at the amount of money spent on airline tickets in the past year, the vast majority of customers will have flown maybe once, twice, 3 times and not spent that much money. And then you get the executive platinums out here in the tail who spend a lot of money with you. Likewise, if you look at Amazon's database, the vast majority of people are probably spending under $100, and then you get some people who spend tens of thousands of dollars. Likewise, when you have a count, so a very common count would be something like the number of times that someone has purchased from you in the past, or the number of flights that someone has taken. Those will also have these right skewed distributions. If you look at the number of children that people have, the majority of people have 0 or 1 or maybe 2 kids, and then you get some very large families out here with 10 kids. So these are all right skewed distributions. Left skewed distributions are also somewhat common in marketing, especially if you do customer satisfaction work. We've already seen an example of a left skewed distribution with the example of how was your experience at CPK? And you'll recall that something like 87% of customers were in the top 2 boxes, 4s and 5s. So the majority of customers were pretty happy. There were a few dissatisfied customers out here in the tail, but hopefully you don't have many customers out in the tail, because if you have too many customers down here, you won't be in business very long. All right, so those are some commonly used names. You should work those into your descriptions of histograms going forward.